Welcome to the next module in graph analysis where we talk about global measures. In the last video we looked at large connected components, so we looked at the size of subgraphs. Now we want to look at more global things where we consider the graphs differently. We introduced already the distance component earlier on where we had the geodesic distance between nodes and their average distance. And what we look here into in the diameter is a little bit different. We look at the maximal shortest path in the graph. So we have the connection from every node to every other node, and we look at what is the maximum that we have there. So we always look at the shortest connection between the nodes and then look at what is the largest number. That is the diameter of a graph. We of course have an infinite diameter if we have a dangling node, because that node is not connected to any other node, and if you recall the geodesic distance, that gives us an infinite distance between the nodes. And if we give that as a diameter for a graph, that conceals relevant information. It only tells us there is a dangling node, but it doesn't tell us how many, how large is the subgraph, and all those things. So the diameter is an important and relevant measure in describing a graph, but it is also one that you have to handle really, really carefully if you have dangling nodes. The path length is also distance-based. You recall the walk on a path between two nodes, and we can look, as earlier introduced already, on the average path length between the nodes and the mean of all the path lengths, depending of what you want to analyze, if you have dangling nodes, if you don't have dangling nodes. And we have also the possibility to look at the average path length. Quite often you see that, where dangling nodes, so the infinite distance, is removed. So you have the average given of all connected nodes. The median path length, as said, avoids such infinity issues in distances, and is therefore also quite often used. We can also look at the density of a graph. This is where it gets a little bit more mathematically now. So the density in a graph is the probability that two randomly chosen nodes are connected. So how likely is it that two people in this network know each other, for example? So, and there is a formula for that. We have the density is m over n over n. So why is that the case? Because m is the actual number of edges that we observe in that network or in this graph, and n over n is the maximal edges in a simple graph that are even possible. So you can also do this by calculating the number of nodes times the number of nodes minus 1. Is also giving you n over n. So if we have a complete graph, the density, of course, is 1. The probability that two randomly chosen nodes are connected is 1. If we have an extremely dense graph, the density is close to 1, so there's a high probability that two randomly chosen nodes are connected with each other. If we have a sparse network, the density falls to 0. The mean degree is also an interesting measure for the global measures. It gives us the mean degree, which is calculated from the degree sequence. So we add up all the degrees that we have in this graph and divide it over the number of nodes. So here it allows us with the mean degree to compare individual degrees of a node to the average or the mean or the median and in this graph. So you can say like this specific node is better connected or less connected to other nodes than the average or the median node in this graph.